Welcome back to this module on exploiting TLP to improve Unicode throughput. In this final lesson in this module, I will give some examples of simultaneously multi-threaded processes. Let's now have a look at some SMT processes, some examples of SMT processes. The first commercial processor that implemented simultaneous multi-threading was the Intel Pentium 4, which entered the market in 2002. It was the first commercial SMT design, and Intel called simultaneous multi-threading hyper-threading technologies. And this table summarizes the sharing possibilities between different thread contexts. Partitions are the return address table, the program counter, the return address predictors, the instruction fetch queue, etc. Fully shared are the caches. The caches are not replicated, because if we replicate the cache, we have a multi-core, which is the topic of a different module. The physical registers are shared between the different hardware thread contexts. The functional units, obviously, that's the whole idea of simultaneous multi-threading. Also the branch prediction hardware and the control logic and the buses. The branch prediction hardware, yes, but not the return address predictors, because that's thread dependent. Furthermore, this is a threshold for the processor scheduler. It doesn't allow one thread to use all the resources, even if the resource is shared. For example, the problem with that is that it may lead to live lock. Some threads will not get executed at all. Therefore, a threshold policy is applied to the processor scheduler. Here's another example of a simultaneous multi-threaded processor, the IBM Power 5 processor. It implements simultaneous multi-threading on top of the Power 4 microarchitecture, and it employs two-way multi-threading, so it executes two threads at the same time. In fact, it supports a simultaneous multi-threading mode as well as a single-threaded mode, an ST mode. In SMT mode, the two threads dynamically share everything there is to share on the chip, whereas in a single-threaded mode, all resources are devoted to executing a single thread as fast as possible. Every thread has one instruction fetch queue, and the dispatch hardware selects in every cycle one of the two queues to decode from based on some priority algorithm. So the instructions fetched, decoded, and dispatched in one cycle are all from the same thread. Only the back end, the execution, is really simultaneously multi-threaded. Furthermore, a thread bit is added to the architectural register number to access the renaming table. In this way, the renaming table is shared between the two threads, and to avoid that a single thread monopolizes, makes use of all the resources so that the other thread is live locked, different threads have different priorities. When a thread uses more than a certain threshold number of reorder buffer entries, then issuing from this thread is stalled, so that the other thread also gets a chance, because otherwise it would not be fair. And we stop thread selection when the thread has exceeded this threshold, when the thread also when the thread has exceeded a threshold number of level 2 cache misses. Then there are so many misses in flight that we must stall this thread, because the hardware is not able to handle more misses, and also the other thread should be able to continue execution when it enters when it incurs a miss, and the threads instructions in the instruction fetch queue are flushed when the thread executes a very long instruction, long latency instruction, for example, when it failed to acquire a lock, which is a very powerful synchronization, which is a synchronization primitive that I will discuss in the multi-core course. To summarize everything we learned about multithreading, I started with software multithreading, which is a very old form of multithreading where process context switches occur each time a process encounters a very long latency event, in particular every time a process does an I/O operation. The main focus of this module was hardware multithreading, and I talked about three forms of hardware multithreading. Block multithreading, also called coarse grain multithreading, where we switch the thread when the thread incurs a long latency event, for example, a level 1 or level 2 cache miss. Fine grain multithreading, where a different thread, instructions from a different thread are fetched and issued every cycle. For that reason, I also call it cycle by cycle interleaving. And the most advanced form of hardware core multithreading, simultaneous multithreading, where we maybe not fetch, but where we issue from different threads in every cycle to get rid of the vertical waste as well as the horizontal waste. Finally, here's a paper that I recommend you to read, a survey of processor with explicit multithreading from my colleagues Theo Ungerer et al. This is a very nice, good summary paper, and I strongly recommend you to look at this paper. Finally, test yourself, and finally some acknowledgement. This concludes this lesson, this module and this course. Thank you for watching. In the next course we will look at advanced memory hierarchy design. Hope to see you back.